Welcome to Brain Vision.
In this problem, we are placing a piece of solid copper on ice in an insulated container, where our ice starts at minus 20 degrees Celsius. And some, but not all of our ice melts. And we want to determine what was the initial temperature of our piece of copper. So the key to this problem is seeing that since not all of the ice has melted, our final temperature of our copper is going to be 0 degrees Celsius. And then we can just say the heat to cool our copper from that initial temperature is equal to the heat to heat that amount of ice from minus 20 to 0 degrees, and then the amount of heat to melt some of that ice. And what data were we given here? The mass of our copper is 6 kilograms, and we'll need some specific heat data and heat of fusion data too. So for copper, specific heat 390 joules per kilogram Kelvin. The mass of ice we started with was 2 kilograms, and the initial temperature of our ice minus 20 Celsius, and we had 0.8 out of our 2 kilograms of ice melts, and the specific heat of ice. So we want to make sure we're considering the specific heat of solid water or ice and not liquid water, since those are different values. 2100 joules per kilogram Kelvin, and then the heat of fusion of water / ice, 3.34 times 10 to the 5th joules per kilogram. Okay, so we can say the heat change going from the copper losing heat temperature, and that heat goes into two things: for our ice to be heated, and then for our ice, some of our ice to melt. And so we need to use two different equations, right? So Q equals to MC delta T for heating with no phase change, and then when we change phase, it's going to be Q equals to M times L, where L is the heat of fusion. And so for our copper, our delta Q copper, then is going to be, so we've got that 6 kilograms, the specific heat 390, and our delta T, so T initial minus 0, so our final temperature for our copper is going to be 0 degrees. And so that's going to be equal to these two terms. So for our ice, we had to heat up our ice, we had 2 kilograms, specific heat 2100, and the delta T 20 degrees there. And then to melt our ice, so it's a 0.8, so we melted 0.8 kilograms, and multiply that by the heat of fusion of water, 3.34 times 10 to the 5th. And so if we solve that for our T initial, we'll get our T initial equal to 150 degrees Celsius, and that would be to 3 significant figures.